Welcome to Brain Vision.
Hello everyone, this is the solution to problem 48, chapter 24 of college physics. This question consists of 3 parts, and in the first one we're going to estimate the distance to a supernova, which is one of the late stages of the lifetime of a star. And so it turns out that these objects emit a ring of material that you can't see until the light of the explosion shines on it. Now we're told that the observation of the ring takes place 1 year after the initial sight of the event. So we know that the time that elapses between seeing the explosion and observing the ring is 1 year, which is 365 days times 24 hours times 60 minutes times 60 seconds. Okay, so that's the amount of time that it takes for light to, or that's the difference between the amount of time it takes for light to just come to us in a straight line, as opposed to going up to the ring and then being reflected to Earth. Okay, we're also told that the angular size of the ring is 81 arc seconds, and 1 arc second is just 1/3600th of a degree. So that's the conversion that we're going to use. But we're told that this is the size of the actual ring. We're not told that this is, the angular size of the radius of the ring. So we need to take half of this, because theta p corresponds to the entire ring, not just half of it, which is what we want to use for our calculation to measure the distance. And the reason we want to do that is because after that, we can set up a right-handed triangle or right-angled triangle here in the ring, in this kind of geometry here, where x represents the distance to us, a is the vertical distance from the star remnant to the ring, and b is the distance from the ring to us. So what happens is that this delta t is actually going to be the difference between times of light traveling along the straight line and the light traveling along the path AB to Earth. So what we have is that this is, let's just say that this is, time 2, which is the second observation, minus time 1, where time 2 is the time it takes for light to go through this path. And so that's A plus B divided by C. And time 1 is the time it takes for light to reach us straight from the supernova. So this is X over C. And here we've, of course, just used the formula that the speed is equal to the distance divided by time. So that's all we used in going from and calculating delta t this way. Okay, so now we know then what kind of geometry we have, and we know that using this relation we can write c times delta t is equal to the distance of a plus b minus the distance of x. So now, in order to use this formula to find what x is, we're going to have to write a and b in terms of x as well. And this is where the fact that we have a right-angled triangle comes in, because we have that x over b is equal to cosine of theta, where notice that theta now is half the parallax angle that we were given for the size of the ring. Okay, so that's cosine of theta. And then we also know that a over x is equal to the tangent of theta. Okay, so now we're putting these two into this boxed equation over here to get that c times delta t is equal to Now A is just x times tan theta. So we have x times the tangent of theta. And we have that B is equal to x over cosine theta, right? So I just multiply this equation through by b, and then I get x is equal to b times cosine theta. And then I divide by cosine theta, and then I get b is equal to x over cosine theta. So I get this is x over cosine of theta. And then, of course, we have minus x. So now the entire right-hand side here is written in terms of x, which we can factorize. So we have x times the tangent of theta plus 1 over cosine of theta minus 1. And that's equal to c times delta t. Okay, so now what we do is we plug in our value for t, for delta t, which is 1 year, and written in terms of seconds is equal to this value. We use the the speed of light, which is just the usual 3 times 10 to the 8 meters per second. So we use this value, and we use this value of the angle theta, which is a half times 0.81 divided by 3,600 degrees. And so if you plug this in, then you get that x is equal to c times delta t divided by the tangent of theta plus 1 over the cosine of this little theta minus 1. And now substituting in the values, you find that this is roughly 4.8 times 10 to the 21 meters. Okay, so we find that the distance to the star remnant or the supernova is roughly 4.8 times 10 to the 1 meters. Okay, so this is part A. Now what about part B? Part B is asking, does this answer make sense? Okay, so for this, you have to know that the size of the Milky Way is roughly 9.46 times 10 to the 20 meters. Okay, so what this means then is that this distance of 4.8 times 10 to the 21 meters is outside of the Milky Way. So indeed, this answer does make sense. And then the last one, the last part is asking you to estimate the error in this calculation. And so that's why I've drawn this little delta theta over here, because you can roughly, just by looking at the picture, estimate what the difference in the angle is going to be between the top of the ring or the middle of the ring and the outside or the edge of the ring. So what I did here, for example, was to say, okay, I know that the angle to the center of the ring is roughly this value of a half times 0.81 divided by 3,600 degrees. Okay, and that corresponds to some value like 5 centimeters, for example, on the image that you're given. Okay, and then you're going to use, so you're going to have something like 5 centimeters is equal to 0.81 arc second. And then if you measure this little distance in terms of centimeters, you find that it's, I don't know, roughly, a tenth of that. So like, let's say it's 0.5 centimeters, which is then corresponding to 0.081 arc seconds. And so basically what you do is you calculate the distance x, now with x max or x min, right? So let's say, and so you're going to use this to be, or let's do x min. x min. And so this is going to be the same calculation, but with a different angle. So here you're going to use c times delta t divided by the tangent of theta plus delta theta, right? And so delta theta is this value. Delta theta is equal to 0.081 arc seconds. And again, you just got this by the ratios, okay? Ratios on the image itself, which you can just take a look at. And then plus 1 over cosine theta plus delta theta. All right. Minus 1. Okay, so calculate this distance. And so here now you use 0.9 arc seconds for this value of theta plus delta theta. And you find out that this value that you calculated is 4.3. Where are we? Okay, so it's roughly 4.3 times 10 to the 21 meters. Okay, so this is the maximum, or the minimum distance to the star. And this is the median distance to the star. So then what we're going to do to find the error is to take the central value and divide the difference between the minimum and the central value by the central value. So in other words, we're going to get that delta x over x is equal to the uncertainty. It's called the relative uncertainty in x. And so we're going to say that this is 4.8 times 10 to the 21 divided, or minus 4.3 times 10 to the 21 divided by 4.8 times 10 to the 21. If you work this out, this works out to be approximately 10%. And so you can estimate, in summary, you can estimate the uncertainty in the distance to the star by estimating the uncertainty in the angle itself, and then just using the maximum or minimum value, or the maximum value of the angle to get the minimum value of the distance. Then you take the difference between the median value, so the black line and the red line. And then what you do is then you divide that by the central value, and that gives you the relative uncertainty in the measurement.